Okay, so today is very exciting. We're going to continue our discussion of the QED, and in particular, let's see, scratched out. What I'm going to discuss today is the renormalizability of quantum electrodynamics, and in particular, what we're going to be doing is discussing more generally the structure of ultraviolet divergences in quantum electrodynamics and arguing that they can all be reabsorbed in a finite number of counterterms, which means that quantum electrodynamics is a very predictive theory in a sense that we're going to make precise later on today. Okay. So let me just remind you of sort of where we stand. Okay, so what we've done is identify 4 ultraviolet divergences in QED scattering amplitudes. And we figured out a way of absorbing these divergences into 4 different counterterms. And associated with these counterterms, we had to impose 4 physical conditions, namely the wave function normalization of the electron and the photon, and physical conditions that define the renormalized mass and electric charge, which allow us to fix the values of these counterterms. And the question then we need to ask ourselves is, if we keep computing in quantum electrodynamics, are we going to continue finding UV divergences, and will we continue having to find other physical conditions we need to impose in order to cure those divergences? So the question is, how many other UV divergent quantities are there? And if there are other UV divergences, can the other UV divergences be cured by these same 4 counterterms? That is to say, when we find other UV divergences, will curing those first 4 UV divergences we've studied already automatically cure all of the other UV divergences? Or do we need more? And you might be forgiven for thinking that because it seems like generically when we calculate a loop diagram in QED, we seem to get a UV divergence. You might suspect that anything you compute will tend to have a UV divergence, and there's no particular reason why just curing these first 4 UV divergences would be sufficient to cure all UV divergences. You might suspect then that quantum electrodynamics is not a particularly useful or predictive theory, precisely because we'll need to introduce an infinite number of physical conditions, an infinite number of things that we have to measure and fix in order to make quantum electrodynamics predictive. Okay. In fact, we'll find out that precisely the opposite is the case, that all ultraviolet divergences in quantum electrodynamics are cured just by, once we introduce those original 4 counterterms, and once we cure the 4 UV divergences that we've already cured, QED is a complete theory with no remaining ultraviolet divergences. This is the property that's known as the renormalizability of quantum electrodynamics. And in the space of quantum field theories, we sharply distinguish between those theories that are renormalizable as opposed to those theories that are not in terms of their predictive power. So what I'd like to do is just begin by considering what possible divergences we could get when we think about generic Feynman diagrams in quantum electrodynamics. So let's consider a random diagram, a Feynman diagram in QED. Okay, so what would this diagram look like? So let's just draw a random diagram to stare at. Okay, so there's a diagram. Okay, let's add a couple of... okay, so maybe we could start with a diagram that looks like this. Okay, maybe it'll look like that, and then we'll add, I don't know, there's a photon. Okay, maybe let's add an electron loop. That'll be fun. Here's, okay, there's another one. Okay, do you want to add something else? Okay, there's another one. Okay, here's some random diagram in quantum electrodynamics. Okay, let's add an external photon. External photons are fun. Okay, there you go. There's a random diagram in quantum electrodynamics. Okay. So what I'd like to do is start thinking about the divergence properties of this Feynman diagram. And so what I'll do is let's let n sub gamma be the number of external photon legs, and n sub e the number of external electrons. And then I'll let p sub gamma be the number of internal photon propagators, and p sub e be the number of internal electron propagators. Okay. And then the question is, what sort of divergence do we expect for this Feynman diagram? So in particular, this Feynman diagram, so let's call this Feynman diagram I. Okay. This Feynman diagram will schematically take the following form. So you'll have a bunch of loop integrals, okay, where you have to integrate over all of the momenta that are undetermined once you impose momentum conservation. Okay. I'll call those K1 up to KL, where L is the number of loops in the diagram. And then you have a bunch of propagators. Okay, so you have a bunch of photon propagators. That'll be like I g mu nu over P1 squared up to I g mu nu over, let's call it, I guess, well, over I p sub n gamma squared, okay, because they are n gamma, p gamma squared, because they're p gamma internal photon propagators. And then you'll have an I over, let's call it, I don't know, what do we want to call it? Let's call it Q/1 minus M all the way up to I over Q/PE minus M, where I'm labeling the different momenta of the internal electron propagators. And so you can see that very schematically, this is a quantity which has some powers of momentum in the numerator, some powers of momentum in the denominator. And we would expect that the divergence of the diagram will depend on the number of powers of momentum in the numerator minus the number of powers of momentum in the denominator. So I'll let D be what's known as the superficial degree of divergence of the Feynman diagram, by which I mean just the number of powers of momentum in the numerator, including, of course, those integration factors, integral d4k, minus the number of powers of momentum in the denominator. So that, using our expression, our schematic expression for that Feynman integral up above, this is going to be 4 times the number of loops minus the number of electron propagators minus twice the number of photon propagators. And so if D is positive, then that means that, at least naively, we expect our Feynman diagram to be power law divergent. So for example, if you had a hard cutoff at some momentum scale lambda, then it would scale like lambda to the d, where lambda is your UV cutoff. If d is equal to 0, then at least naively, you would expect a log divergence, because you would get something like an integral dp over p. And if the degree of divergence is negative, then you would expect that naively, I is UV finite. That is to say, independent of the UV cutoff, and finite when the cutoff is taken away. Now, this is a very naive expectation. Okay. So this naive expectation will be wrong in two types of ways. Okay. So first of all, it may be that you have some special symmetry of the theory, which implies that certain terms in the Feynman diagram cancel. And in particular, as we'll see in a minute, and in fact we've already seen in this class, sometimes there can be symmetries which will lead to divergences canceling even when you wouldn't expect it by naive power counting. Okay. So typically if you have a symmetry, such as gauge invariance or some other sort of symmetry where they're discrete or continuous, that might mean that you have fewer divergences in the theory than you expect, based on this naive counting. And the second way this naive expectation can be wrong is that a naively convergent diagram might contain a divergent subdiagram. And we'll encounter examples of this as we go along. So for example, you might have some Feynman diagram which has got 100 million internal photon propagators, which would give you 1 over 200 million, 1 over p to the 200 million, the denominator, which would make it very convergent. But one of those photon propagators, might get a correction that looks like this, okay, which, as we already saw, was UV divergent. So that would be a case where we have a naively convergent diagram that actually has a divergent subdiagram. Okay. But for the time being, let's just try and characterize in a little bit more detail when we expect this naive power counting to give us a divergence in a Feynman diagram. So, okay, so this degree of divergence, d, was 4L, where L is the number of loops in the Feynman diagram, minus the number of electron propagators, minus twice the number of photon propagators. So let's think of how we can write out the number of loops in our Feynman diagram. Okay, so let's just think about this Feynman diagram for a second. So let's just look at that Feynman diagram that we wrote down up here. Well, in general, when you have such a Feynman diagram, you should think about this as integrating over all of the momenta corresponding to each of the internal propagators. But you have to insert a delta function every time you have an interaction vertex, which enforces momentum conservation for each vertex. So when you think about a loop, each propagator will give you some sort of integral over the momentum of the particle propagating in that channel. But each vertex in the diagram gives you a delta function which enforces momentum conservation. So that means that the number of loops is equal to the total number of propagators, PE plus P gamma, minus the number of vertices. And then you have to take into account the fact that whenever we write down a scattering amplitude, that should be proportional to an overall momentum-conserving delta function. So we should add 1 here. Since we need to pull out of our Feynman diagram an overall momentum-conserving delta function. Which enforces that the sum of all of the incoming external momenta has to be the sum of all outgoing external momenta. So, for example, you could easily draw your favorite tree diagram and compute this and show that, indeed, L would be equal to 0. Okay. And this is here, V is the number of vertices in our diagram. So that, for example, if you want to ask how this scales with electric charge, remember each vertex gives you a power of the electric charge. So our Feynman diagram will be proportional to the electric charge to the V power. So as you add more and more vertices, you're going to higher and higher order in perturbation theory. Everything clear here so far? Any questions? Okay. Now I'm going to use a little trick to simplify this a bit further. So we need to come up with a way of counting the number of vertices in a Feynman diagram. And what we'll observe is that each vertex connects one photon to 2 electrons. So that means that the number of vertices is equal to the total number of external photons, because each external photon has to connect to an interaction vertex, where it connects to up with 2 electrons, plus twice the number of internal propagators, because each internal propagator ends on 2 vertices. And likewise, the fact that each vertex involves 2 electrons means that the number of vertices that, let's say the number of vertices is 1/2 times the number of external electrons plus twice the number of electron propagators. So that we could then go ahead and solve this for PE and P gamma, so that P gamma, the number of photon propagators, is 1/2 the number of vertices minus the number of external photon propagators, the external photons, and the number of internal electron propagators is 1/2 twice the number of vertices minus the number of electrons. Okay, so let's put this all together. So the total degree of divergence of the diagram, at least naively, based on power counting. So that was, remember there was a factor of 4 for each loop because there's a 4 momentum integral, and then each internal electron propagator gives you 1 power of momentum in the denominator, and each internal photon propagator gives you 2 powers of momentum in the denominator. So let's just first use this equation up here. So what is that? That's 4 times PE plus P gamma minus V plus 1. Okay, minus PE minus 2 P gamma. So that's 3 times the number of electron propagators plus twice the number of photon propagators minus 4 times the number of vertices plus 4. And then we can go ahead and plug in these formulas here. So plugging in the formula for PE tells us that the degree of divergence is 3/2 times 2v minus the number of external electrons. And then plugging in our formula for P gamma gives you a v minus n gamma minus 4v plus 4. Now, remarkably enough, you can see the factors of v cancel. You get 3v coming from the p electron, v coming from p gamma, and minus 4v. So what do you get? You get 4 minus n gamma minus 3/2 n electron. So this then is our main result. So it's worth staring at that for a second. What does this tell us? This tells us that the naive degree of divergence of a Feynman diagram, well, it has two very interesting properties. So the first thing to notice is that D is independent of V. Okay. So in particular, that means that it doesn't depend on, if you specify the number of external legs, and the superficial degree of divergence of the diagram doesn't depend on anything else aside from the number of external legs. You could add more and more vertices in your Feynman diagram, but QED has the property that when you add an extra vertex, the additional loop integrals that you need to add get canceled out by the denominators that you need to add when you introduce the additional propagators. So the superficial degree of divergence is a function only of the number of external photons and the number of electrons. And moreover, D decreases as the number of the number of external photon and external electrons are increased. That means that there's only a finite number of possibly divergent amplitudes in QED. Superficially divergent, I should say. There are only a finite number of possible divergent amplitudes in quantum electrodynamics. And that is the property that's what we mean when we say that quantum electrodynamics is normalizable. It means that there are only a finite number of possible UV divergences, so we can absorb them in a finite number of counterterms. And there are only a finite number of physical conditions that we need to fix in order for the theory to be completely predictive. So what I'd like to do now is just very briefly go through the possible divergent amplitudes in QED, and we'll see that in fact all of the possible divergences in QED are precisely those that we already accounted for in the last 2 weeks. Question?
The number of photons is multiplied with the 3/2.
Yes.
It means that we cannot have all the number of...
Yeah, a number of electrons is multiplied.
Number of electrons.
Yeah. Well, there's no rule that says that... Okay. I guess yeah. I mean, yeah, what can I say? Notice that it's impossible to have, by charge conservation, a graph where you have an odd number of electron lines. Okay. So n sub e is always even. Yeah, we'll come into Fourier's theorem is going to arise in just a second. Okay. Yeah, we're going to use Fourier's theorem in just a second. Good question. Any other questions? Okay. So let's just start enumerating the possibly divergent graphs in quantum electrodynamics. There are going to be 7 of them. So let's start with the most divergent possible graph. That would be the one where d is equal to 4. N sub gamma is equal to 0. N sub e is equal to 0. This is a graph which has no external legs. Okay. This is the vacuum energy, and it's unobservable. And in particular, as we've seen several times before, you can just introduce an overall constant term. I guess that's an example of a very simple kind of counter term that you can add in your theory, which will cancel this. So this would be canceled by, say, a vacuum energy counter term. Okay. Now let's look for graphs with a superficial degree of divergence equal to 3. So this would be a graph with one external photon lag. So let's call the momentum of that external photon q. And actually, there are a variety of ways of seeing that although this is naively divergent, in fact, by the symmetries of the problem, it has to be equal to 0. So this is one of the examples of a graph that is naively superficially divergent. You would think it would go like lambda cubed just by naive power counting, but is actually 0 by symmetries. So in fact, there are a couple of different ways of seeing this. So one way of seeing this is to note that that external photon line has to connect to an electron vertex. And so there have to be, so the diagram has to look like this, okay, where this is an interaction vertex, and this is a pair of photon lines. Or maybe it'll help you if I redraw it a little bit. I'll just redraw this a little bit to make it clearer. So it'll look like that. And what is this quantity right there? That's the electron self-energy. That's the electron-electron two-point function. So this is minus IE times, well, if you want to work in position space, an integral d4x e to the I qx of the component of the electron-electron two-point function that couples to the photon. And what is this? Okay, this is the current associated with the electromagnetic field. So what is this? This is the Fourier transform of the vacuum expectation value of the current. Now, if the vacuum expectation, so this is the Fourier transform of the vacuum expectation value of the current. Now, in any Lorentz invariant theory, so remember the current is a 4-vector, and in a Lorentz invariant theory, the expectation value of the current has to be 0. Otherwise, the theory has a preferred direction. So this has to be 0 by Lorentz invariance. So that's one example of a symmetry argument that sets this naively divergent graph to 0. But there's actually a different symmetry argument we can use, which tells us that, in fact, any odd number of currents in a vacuum expectation value, so let's say we have an odd number of currents, has to be equal to 0. And this is known as Furey's theorem. You actually proved a special case of it on the take-home final last semester. And the argument is very simple. The argument that this is true follows from charge conjugation invariance. So just very briefly, the vacuum state has to be invariant under charge conjugation. And by definition, the charge conjugation operator changes the sign of the current. That's what charge conjugation operators do for a living. And so, for example, if you calculate the expectation value of J mu, we can then first use this equation here to write that as 0 C dagger J mu C times 0. And then we can use this second equation here to write that as minus 0 J mu 0. So the expectation value of J mu has to be equal to minus itself. So that's 0. And of course, you can hopefully see that this will generalize pretty easily to any odd number of currents. If you had 3 currents, you would, well, shall I go through it? I think it's reasonably straightforward. In particular, if you take the C dagger, any odd number of currents times C has to be equal to minus that number of currents, because, well, that's what charge conjugation does for a living. So this is sometimes referred to as Fourier's theorem. It's a good name for a theorem. Okay. So let's continue with our discussion of divergent diagrams. Before I continue, I actually want to make one more point, which is that what we're going to do is restrict our attention to one-particle irreducible Feynman diagrams. Why is that? Well, in principle, we could consider any Feynman diagram. But if a Feynman diagram is one-particle irreducible, then that means that if you want to calculate its superficial degree of divergence, let's say it's not one-particle irreducible. That means the Feynman diagram has a form like this, where we can cut on a line here and it'll fall into 2 parts. So we could compute the degree of divergence of this reducible Feynman diagram by just taking the product of the degree of divergences of the individual one-particle irreducible diagrams. So we'll just think about one-particle irreducible diagrams. That's sufficient to find all of the divergent amplitudes in the theory. Okay. So let's keep enumerating the possible divergences in the theory. So remember, the superficial degree of divergence was 4 minus the number of photons minus 3/2 times the number of electrons. So we did d equals 4, d equals 3. Now let's do d equals 2. So at d equals 2, the only diagram we have with a superficial degree of divergence 2 is one with 2 photons. And here, actually, let me redraw this. I'll use this. So this will be so we'll be considering the diagram, a one-particle irreducible diagram with 2 external photon lengths. Okay. And naively, this would be something that's quadratically divergent. In particular, this is a symmetric 2 tensor. Okay? And as we saw, there are, in fact, 2 different symmetric 2 tensors that one can construct given the momentum of the external photon here. So naively, one might expect that you could have an arbitrary linear combination of those 2 tensors. So you might expect 2 quadratically divergent terms that we could have contributing to this diagram. However, we know by the Ward identity that if you contract this guy with p mu, it has to be equal to 0. So that means that you're only allowed to get a particular linear combination of those two tensor structures. And so, in fact, you only have one potentially divergent quantity, which we call pi. Okay. One other comment that I'll make is that pi needs to be finite as p squared goes to 0. So pi should be finite as p squared goes to 0, because otherwise this diagram would have a pole otherwise the two-point function would have a pole as p squared goes to 0, which would look like some sort of massless intermediate state. And the electron has a mass. So we would expect that pi should be finite as p squared goes to 0. And so that means that when you compute these one-particle irreducible Feynman diagrams, you actually have to pull out 2 powers of the momentum here, to give you that factor of g mu nu p squared minus p mu p nu, so that pi is not going to be quadratically divergent, as you might expect, based on this naive degree of divergence, but because you have to extract 2 powers of the momentum, pi is in fact going to be logarithmically divergent. So pi of p squared, then, you could imagine, for example, Taylor expanding in a power series in p squared, and you would get pi of 0 times something that's logarithmically divergent. And then the first term would be pi prime of 0 times p squared, but again, if you extract, every time you extract a power of p squared, you reduce the degree of divergence by 2. So you'll get other terms that are finite as you take the UV cutoff away. So in particular, at d is equal to 2, you have UV divergence. But because of the Ward identity and the fact that there are no massless intermediate states, it's actually only logarithmically divergent. And the important point is that the logarithmic divergence is not a function of p squared or x or anything like that. It's just a number. Okay. So we get one number. And indeed, it's a number that we've already computed about 2 weeks ago, at least in the one-loop approximation. But now we see that the answer that we got, and indeed the answer that we got was a divergence time, a number times log lambda. And we see that that was a general consequence of the symmetries of the problem and this sort of this general power counting structure. Okay, let's continue. So at d is equal to 1, you can finally get diagrams with electrons. So for example, you can have a diagram like this. So that is what we called sigma, okay, the 1pi contribution to the electron self-energy. And again, we can imagine expanding this in a power series in its argument. Okay, remember, sigma was a scalar function that we wrote as a function of p slash. So it's got to be sigma of 0 plus p slash times sigma prime of 0 plus dot dot dot. And every time you pull out a factor of the momentum, the degree of divergence of your Feynman diagram decreases by 1. Okay? Because that means that there's one momentum that gets pulled out of your Feynman integral that can't contribute to a potential divergence when you do a loop integral. So in particular, you expect now 2 divergent constants, sigma of 0, which should be linearly divergent, and sigma prime of 0, which should be logarithmically divergent. Okay. I mean, is this clear that every time you pull out a factor of the momentum, you decrease the degree of divergence? I mean, one quick and dirty way of seeing that, if that's not clear, is you could just imagine taking sigma of p and Taylor expanding around p is equal to 0. And sigma prime of p is a d by dp of sigma of p, evaluated at p is equal to 0. And every time you have a, so for example, sigma prime of p slash involves, a lot of a d by dp slash of a bunch of quantities, one of which will have something in a propagator that looks like k slash plus p slash or something like that, and then you'll get a 1 over k slash plus p slash squared. Okay, you'll get that kind of thing going on. Every time you take a derivative, you pull down additional factors into the denominator. So is more convergent. Okay. Actually, I'll make one brief comment. So actually, it turns out sigma of 0 is going to be log divergent rather than linearly divergent. And that is, again, because of a symmetry of the theory, which is known as chiral symmetry. I believe I discussed chiral symmetry when I introduced Dirac spinors last semester. I hope. Do you guys remember that? Okay. If I didn't, I think I discussed it only very briefly. Let me remind you. If I'm still getting blank looks, then I know what problem to assign for the problem set for next week. Okay. So in particular, remember that sigma of 0 is interpreted as a mass shift, a shift in the mass of your electron. Since, your electron two-point function, which we call g, was like 1 over p slash minus m minus sigma of p. So at p goes to 0, you would just interpret this as a shift in the effective mass of the photon. But the point is that when the mass of the electron, when the mass of the electron is equal to 0, your theory actually has a new symmetry known as chiral symmetry. Did I not do this last semester? Okay. So a massless Dirac fermion has a symmetry. So if you take, psi to e to the I alpha psi is the usual symmetry that, the usual charge symmetry, the usual U1 symmetry associated with the charge of the electron. You can actually put a factor of gamma 5 here, and that will still be a symmetry of your theory, but only when the mass of the electron is equal to 0. So that means when the mass is equal to 0, sigma has to be equal to 0. So then you could imagine Taylor expanding sigma in powers of the mass. And because you know that sigma has to be 0 when mass is equal to 0 by chiral symmetry, sigma of 0 has to be proportional to the mass. Mass has the same dimensions of energy and momentum. So that means that you have to pull out one additional factor of m, which reduces the degree of divergence of this Feynman diagram from linearly divergent to logarithmically divergent. So sigma of 0 has to be proportional to mass times log lambda, since as m goes to 0, sigma of 0 has to be equal to 0. So I know I discussed chiral symmetry last semester, but it might have been very, very briefly. So I should probably come up with a good problem for you guys to do for next week on that. But this is yet another example. This is now like the third or fourth example we've seen where a symmetry of the theory leads to a Feynman diagram being more convergent than one would expect. And indeed, if you go and look through your notes, when we calculated the electron self-energy last time, we found indeed that there were two divergents. There were sigma 0 and sigma prime of 0, which we absorbed by the two counter terms, the mass normalization and the electron wave function normalization. But both of those were logarithmically divergent, not power law divergent. Okay. There's one other graph, which is divergence with degree of divergence 1. That's the photon 3-point vertex. And again, as we mentioned earlier, by Furey's theorem, this has to be equal to 0. Okay. As you checked at one loop on the exam last semester. Okay, this is again by charge conjugation invariance. And finally, at degree of divergence 0, remember the degree of divergence is 4 minus the number of photons minus 3/2 times the number of electrons. We have this diagram. And it turns out that this diagram, even though it's naively logarithmically divergent, also has to be finite, rather than not 0, but finite by symmetries of the theory. Now, actually, I was going to have you prove this on a problem set, but I already had a really good problem for you this week, so maybe you'll do it next week. But the basic way, one way that you can see that this is finite is by gauge invariance. Okay. And this is a kind of sneaky way. This is a very sneaky argument. Basically, the point is that if this diagram were divergent, then we would need a counter term to absorb the divergence. And that counter term would have to be proportional to a to the fourth. But there's no gauge invariant combination of the electromagnetic field strength A that you can write down that looks like a to the fourth without any powers of the momentum. Okay. So, I mean, that's a very sneaky argument, but it does mean that if the theory is gauge invariant, you can't possibly have a divergence in this term. To some extent, I don't like that argument because you should really be able to check or prove gauge invariance directly using Feynman diagrams. And indeed, maybe now I feel like next week for one of your problems, I'll have you check at one loop explicitly that this diagram is finite rather than divergent. It's not too hard. So, but just to summarize, we've written down all 7 possibly superficially divergent diagrams in quantum electrodynamics. Only 3 of them were actually superficially divergent once we took into account the symmetries of the theory. And the divergences could be incorporated in terms of 4 constants. Oh, I'm sorry. I forgot one example. Okay. Anyone know what example I forgot? There's another diagram with degree of divergence 0. Yes. Okay. Right. So at d is equal to 0, you have the electron vertex. Okay. Right. D is n4 minus n gamma minus 3/2 n electron. 2 electrons, 1 gamma, degree of divergence 0. So this is proportional to IE gamma mu, because that's the only thing you can write, which is 2 spinors and 1 vector index, times something logarithmically divergent. Okay, plus finite terms. And indeed, this is the logarithmic divergence that we incorporated in one of the form factors. So in particular, this is what we called minus IE. Just put a minus sign there, gamma mu. And then gamma mu is equal to, let's see, I forgot to write this in my notes, but that's okay. Gamma mu times that first form factor plus I sigma mu nu over 2m times p nu. So this is, I guess, p is the momentum of that electron, times the second form factor, p squared, p. And then you can see that F2 has to be finite, because we've pulled out a factor of p here, which reduces the degree of divergence by 1. And F1 is going to be logarithmically divergent. So F1 of p squared is F1 of 0 plus p squared times F1 prime of 0 plus dot, dot, dot. And this guy is going to be logarithmically divergent. And this guy and all of the other derivatives will be finite. And indeed, when we went and we calculated the anomalous magnetic moment, one of the lucky things about that was that the anomalous magnetic moment, F2, was actually UV finite. Okay. I didn't tell you why it was UV finite, but now you see why it's UV finite. We didn't actually bother calculating F1 because I got sick of calculating these Feynman diagrams. But if we had, we would have found that it's UV divergent. Okay. So what we found is that there were 3 superficially divergent Feynman diagrams, the 2 electron and photon self-energy and the electron vertex. And the divergences could be incorporated into 4 constants. And indeed, this is precisely the number of counterterms that we introduced above. And so, that means that all of the counterterms that we introduced over the last 2 weeks are sufficient to absorb all of the naive divergences in the theory. Any questions on this before I continue? So there's a few subtleties that I think are worth discussing. Okay, maybe I should pause and see if there are any questions.
So we're only investigating diagrams of down to b equals 0.
Yes.
But what if there was some funny theory out there that had some funny property that made it so that there were actually diagrams whose degree of divergence were greater than the superficial degree of divergence calculated from its...
Okay, a funny theory such as QED, which is okay.
So
That's the next.
great. Okay, perfect.
Yeah. Okay. So in particular, in QED, all, let's say, superficial divergences can be absorbed by 4 counterterms. That basically means that you can make 4 measurements, okay, and from that make an infinite number of predictions. However, as we mentioned earlier, and as we'll discuss more now, there are, of course, diagrams that are going to be superficially convergent, yet still divergent. Okay. So there are some diagrams which are superficially convergent, but still diverge. And the remarkable claim, and this is actually highly non-trivial, is that nevertheless, all of the divergences still cancel using only those original 4 counterterms. As long as we cancel the UV divergences of the superficially divergent diagrams, all of these non-superficial, I don't know, what's the opposite of superficial? All of these non-superficial, all of these deep, I don't know, I don't know what the opposite of non-superficial is. Subficial, maybe? All of these subficial divergences cancel as well. Okay. Now, if you think about it a little bit, this is obvious. But if you think about it more than a little bit, it's actually completely not obvious. Okay. So, so if you think about it just a little bit, okay, the sort of diagram that you might write down, okay, so what's something that would be nice and finite? Let's say we have four electron legs, okay? Okay, that's going to, 4 external electrons is finite. Okay, the degree of divergence is -2. Okay, so naively it's finite, but you could imagine, say, that one of those photons contains an electron loop in it. Okay, so this guy here, this is a divergent subdiagram. But when you calculate the full 4 electron scattering amplitude, you'll need to subtract off a counter term. Okay. You'll need to subtract off the counter term, you know, the corresponding sorry, that's a little messy. It's still a little messy, but, you know, whenever you calculate say, the 4 electron scattering amplitude, you would also have to include the corresponding counter term. And remember, that counter term is designed to cancel the divergence in the photon self-energy in the photon propagator. And so clearly, if you include the photon propagator as just some subdiagram, then the divergences will cancel there as well. Okay. So that's an obvious cancellation. Obvious cancellation. Okay, so if you don't think about it anymore, then it's obvious. Okay, but it turns out that if you think about it a little more, which is that there are other diagrams okay, which have so-called overlapping divergences. So, for example, I don't know. So let's take, so here's an example. So this is a divergent amplitude, and then, so what is an overlapping divergence? Okay, that's when 2 divergent loops share a propagator. So for example, over here you have this divergent loop right there. Here you have this divergent loop right there, but they share that photon propagator. Or you could imagine something like this. Here, these 2 divergent loops share this propagator between these 2 points right there. So those are both examples of overlapping divergences. The cancellation is not obvious. And in fact, it's a sort of deep result, okay? Not one that I'm going to prove, which is known as the BP-HZ theorem. Which states that in any theory with a finite number of superficially divergent amplitudes, all divergences are removed by the counter terms that cancel the superficial divergences. So this means that it's sufficient to only consider those superficially divergent diagrams. And in particular, it means that QED is really a completely finite theory once we include those four counter terms. So this is like a highly non-trivial result. It's not in the textbook. I think it's probably in Weinberg. Most things are. But it's not something that I was planning on proving here. There's a question? Yeah, that's right. That's right. Okay. Yeah, okay, fine. There. Okay. Oh, wait, no, that's 5. That's Furry's theorem. Okay, there you go. Good. Okay, yes. Yeah, no, I was being a little sloppy there. Yeah. Okay, so that, yeah, so everyone got that question. So the one that I drew, both of those diagrams there actually are contributions to the electron and photon self-energy, so they're included in counter terms. But yeah, but you could certainly add more legs so that they wouldn't be included in the counter terms. Yeah. Good. Other questions? Okay. So this is a remarkable result. Okay? It's not something I'm going to try and prove. Instead, what I want to try and do before the end of class today is consider a little bit more generally the space of quantum field theories and whether we expect this remarkable property that all UV divergences can be canceled by a finite number of counterterms for other classes of theories. Okay. So let me just give you a simple example. Okay. So let's consider the generalization of quantum electrodynamics to d space-time dimensions. So how would our calculation change? So the naive degree of divergence, remember, it got a positive contribution for every loop integral. It was 4 times the number of loops because you would integral d4k for each loop. In d space-time dimensions, you'll have d times the number of loops. And then you still have propagators that go like 1 over p for electrons and 1 over p squared for photons. And so then, if the electron vertex if each vertex connects 1 photon to 2 propagators, all of the counting that I went through earlier goes through. And so it's a straightforward thing to go ahead and chase through that computation I did earlier. So in particular here, let me just scroll up and show you that computation. So this is the miracle computation right here. And you can see that it was this 4 that appeared right here that led the factors of V to cancel. So it's because you're considering quantum electrodynamics in 4 dimensions that the answer that we got for the naive degree of divergence was independent of the number of vertices. So if you just go ahead and put in a power of d here instead of a power of 4, you could just go ahead and write down the answer. I'll just write it down for you. You get d plus d minus 4 over 2 times v minus d minus 2 over 2 and gamma minus d minus 1 over 2 n e. Okay. So I didn't actually go through and plug in the numbers and compute it all out for you. You have a problem on the problem set that I'm just handing out. We'll do basically that, in a slightly different problem. But basically that computation. And so now, however, this result tells you something really interesting. Because this tells you more generally what kind of things can happen for more general types of quantum field theories. QED in d dimensions being an example of this. So what happens is that when d is equal to 4, the degree of divergence is independent of the number of vertices. All we had to do is specify the number of external legs, and then that was enough to determine whether the diagram was divergent or not. In more than 4 dimensions, the degree of divergence, if you fix the number of legs, that is, you fix the amplitude you're interested in, then as you go higher and higher order in perturbation theory, there'll be more and more vertices, and eventually your diagram is going to diverge. So, in more than 4 dimensions, all scattering amplitudes diverge. At sufficiently high order, in perturbation theory. So let's contrast that to the d equals 4 case, where the degree of divergence was independent of v. So when the degree of divergence was independent of v, a finite number of scattering amplitudes diverge. Now let's think about what happens when d is less than 4. When d is less than 4, not only do only a finite number of scattering amplitudes diverge, but only a finite number of Feynman diagrams converge. Because let's consider a particular scattering amplitude, with 1 vertex, 2 vertex, 3 vertices, and so forth. As you start increasing the number of vertices, the diagram gets more and more convergent, rather than more and more divergent in the case of d bigger than 4. So not only do only a finite number of amplitudes diverge, only a finite number of diagrams diverge. Okay.
True for any field theory, the generalizable in 3 dimensions, generalizable in
Probably. I believe that's a true.
Here where
I believe that's a true. That's naively a true statement. Because remember, things diverge because of the loop integrals. If you reduce the number of dimensions, you reduce the degree of divergence. So I believe that's a correct statement. Right. So I think that's a true. Yeah, you have to decide how do you compare field theories in different dimensions. You have to just say, maybe you have to be precise about exactly what you mean, but
That's
just
what
naively that's a true
the
statement.
example I would think would always work in either field theory or quantum circle.
Yeah.
You should always go for the
That's right. That's right. Yeah, maybe I can just sort of conclude this discussion with a bit of a summary. Okay. This is really more or less a definition. So when we think about field theories, we really divide the world of quantum field theories into 4 different classes. Okay. So first of all, a quantum field theory, the simplest possible case is where there are no UV divergences. In this case, you say that the quantum field theory is finite. So that's the case if no diagrams diverge. So we saw that if you have symmetries, that can make naively divergent diagrams finite. And so typically finite theories are theories with a huge amount of symmetry. We won't really be considering any in this class, but there are some that you've considered in your previous classes. You know, think of okay. So quantum mechanics is a 1 plus 0 dimensional quantum field theory. Quantum mechanics has no UV divergences. Quantum mechanics is a finite quantum field theory. That was sort of a trick question. Okay. The next simplest case is a field theory like quantum electrodynamics in less than 4 dimensions. We call those theories super renormalizable. And that's the case where you have a finite number of diagrams which diverge. I guess I should say superficially diverge. A renormalizable theory is one where you have an infinite number of Feynman diagrams which diverge, but only a finite number of scattering amplitudes diverge. So for example, in quantum electrodynamics, you take the photon self-energy. It diverges at all orders in perturbation theory. Higher and higher loops, you keep finding more and more contributions to that divergence. But there are only a finite number of diagrams that diverge, and only a finite number of constant divergences that you need to cancel by the introduction of countergenes. And finally, a quantum field theory is non-renormalizable if all scattering amplitudes diverge. Maybe I should, well, okay. Any questions on this? You know, if you read like old-fashioned books on quantum field theory, they'll tell you that non-renormalizable theories aren't good for anything, they don't make sense. That's not actually true. I mean, it's just that they're not quite as powerful and as useful as theories like quantum electrodynamics, where you only need to introduce a finite number of countergenes. So we'll actually spend some time talking about non-renormalizable field theories as well. But of course, the ideal situation is one where you're considering a renormalizable field theory. Good. Any questions? Yes. All scattering amplitudes diverge. I suppose, yeah, except for those which have to vanish by symmetry, I would suppose. But, you know, for example, if you look here, when D is bigger than 4, fix NE, fix N gamma, so fix the amplitude you're looking at. Take V to be large, then the D, well, goes to infinity.
Yeah, but the question is whether it's all or infinite number. So if you take a
Well,
lot of
let's put it
lines-
this way. All superficially diverge. Does that make you happy? I mean, it could be possible that you could have a non-renormalizable theory with a symmetry which makes some diagrams vanish, but except for that case, you know, they would all diverge.
So it's not possible to have some finite
No, plenty of diagrams will be finite, but the amplitudes will not be finite. The amplitude being the sum of all diagrams. right? An amplitude, you fix the number of external legs, you sum over all possible diagrams. And the point is that at sufficiently high order in perturbation theory, you'll always get a divergence. Yes.
So when you were talking about the dependence of the degree of divergence of the number of d, the number of dimensions, I would think at first that that little d is just the number of. We only care about the number of non-compact dimensions because otherwise, well, okay, we have no more than 4 dimensions.
Yeah.
But what we really care about is high energy physics here, right? So we're looking at UV divergences.
Yeah. Good. I mean, that's a good question. That's a good point. I mean, the point is that, you know, here I'm making a very sharp distinction between normalizable and non-normalizable theories. But yes, I mean, the point of a renormalizable theory is really, yeah. I mean, this gets into the question of effective field theory, which is the next thing that we're going to be discussing. The point being that, let's say we really live in 5-dimensional QED. But there's a circle that's very, very small and we can't see it. That means effectively we're in 4-dimensional quantum electrodynamics. And so your worry is really that, well, one of those is renormalizable and the other one isn't. The point is that even a non-renormalizable theory can look like a renormalizable theory in some sectors. And once you have a sector, say at low energy, that looks like a renormalizable theory, then the theory is predictive up to some energy scale. And the energy scale associated with that breakdown is going to be the scale where, you know, this extra physics becomes apparent. Any other questions? Let me end here with one final bit of numerology. So let's consider again our example of quantum electrodynamics in d dimensions. So quantum electrodynamics in d dimensions is a theory of an electron and a gauge field along with an interaction term that is, well, the electric charge times A mu psi bar gamma mu psi. So let's just do a little bit of dimensional analysis with this formula here. So what is the dimension of the vector field, the gauge field A? Well, remember that an action is d is dimensionless because we have to exponentiate it for it to appear in a path integral, which means that the number of mass dimensions of a Lagrangian has to be d because you integrate it d4x in dx in order to get something that's dimensionless. So here, brackets denote the number of mass dimensions. What's the dimension of A? Well, the action contains a term like f squared, which is a derivative of a squared. Derivative has mass dimension 1, so that being equal to d implies that the dimension of A mu is d minus 2 over 2. You have to subtract off 2 because there's 2 derivatives and divide by 2 because there's 2 a's. Likewise, a kinetic term of the form psi bar d psi has to be dimension d. That implies that the dimension of psi is d minus 1 because you have to subtract off the derivative over 2. And so then the statement that E A mu psi bar gamma mu psi has dimension d Well, you know what the dimension of A is. You know what the dimension of psi is. So that tells you the dimension of E. So that means that the electric charge is a dimensionful constant. And just by dimensional analysis, its dimension has to be, let's see, 4 minus 3/2 d minus 2. Otherwise known as 6 minus 3/2 d. Okay. So in 4 dimensions, the electric charge is dimensionless. And in more than 4 dimensions, the electric charge has a negative number of units of mass dimension. It scales like mass to some negative power. And in less than 4 dimensions, it scales like mass to some positive power. So in particular, what we see is that when the coupling constant of our theory, which in this case is the electric charge, has positive mass dimension, the theory is super-renormalizable. When the coupling constant is dimensionless, the theory is renormalizable. And when the coupling constant has negative dimension, scales like mass to some negative power, the theory is non-renormalizable. This is not an accident. Okay. The dimension of the, so one way of characterizing theories, the renormalizability of a theory, is to look at the dimension of the coupling constant. So you'll work this out, okay, you'll work this out in great detail on the problem set. But we'll see that this is really just not an accident. Okay? Renormalizable theories, super-renormalizable theories, are those where the coupling constants have positive mass dimensions. I'm out of, was there a question? Oh, wait, what did I get something wrong? Oh, D, shoot, sorry, wait. I totally got this. Okay, what is that? 4 minus d over 2. Yeah, good. Okay, sorry about that. 4 minus d over 2. Wait, did I get this wrong here? 3/2 minus 1/2. Yeah, no, okay, good. Thank you. Sorry about that. This is what happens when I wing it at the end of class. Okay, any other questions? Oh, good. Okay, I will see you on Tuesday.